Welcome back. This can be the last lecture in this time series course. I'm going to touch on one section out of chapter 11, which is really all about advanced models in time series. This particular model gets used quite a bit in marketing and advertising, and therefore I feel like we ought to include it. Up until now, we've been talking about having a single outcome variable that's our time series variable. So for example, the most common one is sales. In this particular chapter, we've been studying how various covariates, especially advertising, affects this outcome that we care about. But sometimes the variables have relationships that affect each other. So I mentioned in a previous video that the advertising budgets, the way companies actually do advertising budgets, is to set it as a fraction of sales. So if my sales are high in a previous period, then my advertising next period will be higher. If my sales go down, then the advertising budget goes down as well. So in some situations, you might have advertising being affected by sales as opposed to the other way around. We're very interested in these sorts of causality questions. The tool that we're going to use to handle this is called a vector autoregression model. And so the idea is going to be simply this. All the variables get treated symmetrically. All the variables are going to be endogenous, so what that means is going to be within the system. I've stripped down the notation out of the textbook. Let's say we've only got two variables. This could be expanded to more than two, but for starters, let's just have two variables. So we could think of y as being our sales, and maybe x is the advertising. I'm going to assume an AR1 model that is a function of both advertising and sales. My sales at time t will be some function of my sales in the previous time period, as well as what my advertising was in the previous time period. Likewise, I'm going to say that my advertising this period depends on both what my sales were in the previous period. So if my ad budget is set by percentage of sales, then this model makes a lot of sense, as well as allowing for the possibility that my advertising last period is associated with my sales, my advertising this period. In order to fit these VAR models, both x and y are going to have to be stationary. So if they're not stationary, we need to take differences. Then basically what we do is we estimate these two models with OLS. Now, I'd like to just mention a nice benefit that we get from doing these models, and it's a concept called Granger causality. So Granger causality allows us to make inferences about whether advertising causes sales or sales causes advertising, or both or neither. Remember what we need for causality. We need association, or concomitant variation is what I called. And so what that means is we have to have a significant coefficient of one of these. We also need time order of occurrence. So time order of occurrence is pretty clear in this model, where whatever is happening in time period t is a function of stuff that was happening in previous time periods. The hard one is time order of occurrence. And so we're not going to call this causality, we're going to call it Granger causality, because it takes a lot of additional effort to rule out additional causes. And sometimes that might take years and additional studies. The four possibilities with Granger causality are either x is causing y. Now, if x is causing y, then what we would expect is that the beta 1 up in this regression model had better be non-zero. So that is saying there's concomitant variation between y this period and my x in the previous period. And we can see that there's time order of occurrence there as well. Now, the other thing we expect is that phi 2, so phi 2 is sitting right here, ought to be 0, meaning my sales in the previous period shouldn't be affecting my advertising this period. So if these two conditions hold, then we would say that X is likely causing Y. Well, what happens if it's the other way around? So what I mean by that is this beta 1 is now 0. So advertising doesn't affect sales, but E2 is non-zero. Well, my sales in the previous period affects my advertising budget this period, then I would say that sales is affecting advertising. What if both of these are non-zero? Well, then we're going to say that there's bidirectional causality. What we would say from this is advertising affects sales. What we would say from this coefficient is that sales also causes advertising. Often when you have a situation like that, there's really a third variable that's driving both of them. That's always a possibility. So maybe when the economy is booming, we're flush with cash, so we advertise more, and it's really easy to have higher sales. When the economy's in recession, things are bad. So there's probably a third variable that's driving both of these. Finally, if neither of these are different from 0, then there's no causality because we don't have any association, no concomitant variation going on. We need to know how many lags to use. So what we typically use is AIC corrected or some other measure. Let's go do Lydia Pinkham again. In order to fit a VAR model, we need to use the VARs library. And the first thing that we're going to do is use the VAR select model. So VAR select is going to help us choose how many lags do we need in here. So right now I only have one set of lags. It could be that I need more lags than that. So let's go set this running. What we see here is that these measures are saying somewhere between 1 and 3 lags. Well, I'm going to go try a model with 1 lag in it, and we will fit that with the var function. Let's give it a try. And after you fit one of these, there's a test that we can do to determine whether this is adequate. So this serial.test, and this is the portmanteau test, you're going to see it's borderline significant. I'd love to have this a bit larger, but it's borderline significant. We could go try 2 lags. So if I do 2 lags, you're going to see now it's borderline significant in the other way. If we do 3 lags, it's nowhere near significant. So if we did 3 lags, we'd really have it. I can just do a summary on it. And what we'll see is output that is pretty similar to what we're used to with regression. We first have a model predicting advertising this period as a function of advertising in the previous period. So we get a big positive coefficient there. We get a borderline significant negative coefficient, 2 periods lagged. 3 periods lagged, it's kind of borderline significant as well. I'm not completely sure we need those, but our previous tests were saying we ought to be including those lags. Likewise, we see a strong effect for sales. So both advertising and sales have a positive effect. These are lagged versions, affect my advertising this period. So both of those are very highly significant. The sales 1 period lagged is also significant. So it looks like whatever my sales were 2 periods ago actually has a negative association with my sales this period. So maybe that's capturing either some forward buying or some cyclical effects. I'm not quite sure. If we keep scrolling down, now we get the models for sales. So sales we see as affected by sales in the previous period, the lag version of that, and that's about it. Nothing else is entering into that model. The next thing I'd like to do is a Granger test. But the Granger test in this situation is substantially more complicated because I have 3 lags. And so as a little review, I want to find out whether X has an effect on Y or Y has an effect on X. So I have a model something like this. X sub t, where this is my advertising variable, is equal to, say, beta naught plus beta 1. I need to get some names for these coefficients. Let's say this is x t minus 1, so that's the lag 1 version, plus, let's say beta 2 x t minus 2 plus beta 3 x t minus 3 plus, okay, beta 4 y t minus 1, beta 5 y t minus 2 plus beta 6 times y t minus 3. So what I'd like to understand is whether I need these three coefficients. So does sales in any way affect my advertising? So I'd like to test the null hypothesis that beta 4 equals beta 5 equals beta 6 equals 0 against the alternative that at least one of beta 4, 5, 6, non-zero. So maybe I should put betas there. One of those betas is not equal to 0. So in English, this means sales no effect on ads. Here, sales has an effect on ads. Well, how do I do this test? I'm going to do it using the general linear hypothesis test. So I'm going to go fit the full model, and then actually what I'm doing here is I've got sales as the dependent variable instead of advertising. And so now I've dropped advertising from the model. This is the model. Back in machine learning, we called this the reduced model, which is how does sales alone without advertising affect sales? We can do the test using the ANOVA command. Let's go take a look at the ANOVA command. What we see is that if we compare the model with 3 lags, so this is 3 lags of both, I'm kind of missing the other part of it, here it is, versus the reduced model that gets rid of advertising, the p-value is very large. So 0.1559 is saying I cannot reject the null hypothesis that these 3 coefficients are not necessary. So notice this hypothesis has 3 degrees of freedom. It says this model 1 is not worse than model 2. What this really says is I can I don't have evidence to say that advertising is related to sales after I've been controlling for my sales in the previous periods. This is not looking good for advertising. Well, let's go do this for advertising now. So same thing. Here's advertising as a function of all 6 predictors. Then we will fit advertising as a function of only my 3 advertising variables. And let's go run ANOVA. So the ANOVA is saying I've got a very significant coefficient suggesting that sales in my previous periods is related to my advertising this period. By getting rid of those 3 predictors, so lag sales 2, lag sales 3 periods, my sums of squares would increase by a lot, giving me an F statistic. If you divide this by the mean squared error, you get that F. I'm going to reject the null hypothesis that these 3 coefficients are all equal to 0. My conclusion is sales is affecting advertising. What we should conclude then is unidirectional causality. I can't reject the possibility that advertising has no effect on sales, but sales in previous periods is affecting my advertising this period. Not good for the advertising people at Lydia Pinkham. I want to do one more thing with us. We can include exogenous variables in a var model. So these are variables that are not affecting one another, but they are things that have happened outside of the system that could affect the variables in the system. So a great example of this is prohibition. What effect did the fact that alcohol became illegal during prohibition have on both the advertising and the sales of Lydia Pinkham data? When we do this in R, I include a new argument called exogenous, and I can list various variables here that I want to throw in as additional predictors in these models. So if I go look at my serial test, it's borderline significant with 2 lags. Let's go with it for now, and I'll show you what we end up with. So let's start with this first one. How did prohibition affect our sales? The answer is maybe it has a small positive effect. So the p-value is borderline significant. During prohibition, after controlling for advertising and sales, it looks like maybe my sales go up by 149 or so, but it's a borderline significant result. On the other hand, let's go look at how prohibition affected advertising. And what we're going to see is a very strong positive effect. So during prohibition, advertising budgets went up by 212 on the average, and that's very highly significant, suggesting that Lydia Pinkham knew what they were doing. They wanted to sell more of their alcoholic elixir, and that's why they started increasing their advertising budgets during prohibition. That gives you a little bit of a sense for how we would use var models. I'd like to mention one other example. This example comes from a paper that I worked on a couple of years ago. And so I've put this out on Canvas. This paper tries to understand the dynamics of customer engagement with mobile technologies. So I'd like to tell you a little bit about Air Miles. Air Miles Canada is a loyalty program, and people join the program and accumulate points whenever they shop. So if they buy gasoline for their car, they can accumulate points. If they go shopping at the mall at certain stores, they can accumulate points. When they go grocery shopping, they accumulate points. They can redeem those points, various rewards ranging from lift tickets to gift cards to airline tickets. So all of these things are ways of experiencing the brand by getting a reward. Now, Air Miles Canada at some point launched a mobile app to try to gamify the process of getting points. So you could download their app on your mobile phone and check in at an Air Miles sponsor. You could check your balance. You could look at what sorts of things you could redeem your points for. And what we suspected would happen is a dynamic system where the more you accumulate points, maybe the more you want to check your phone and see how many points you have. And the more you check your phone, the more you check in, hopefully the more points you have. And so these things should reinforce each other. Then likewise, we would hope that there would also be a possibility that the more points you have, the more redemptions you get. Of course, if you get a redemption, that might cause you to want to accumulate more points. So I just got a free toaster. Maybe I want to use my Air Miles card more in future purchases so I can get a TV or a lift ticket or something. We wanted to investigate how these three things affected each other. Did these create sort of a virtual circle where I accumulate points, makes me want to use my phone more, and those reinforce each other, and then I get I redeem for something, and that reinforces these other behaviors. So this is really a classic situation for a VAR model. You can see our model here. We actually had 4 variables in this model. So this is how long has it been since you've used the app, so recency. This is how many times did you use the mobile app. So you have kind of 2 flavors of your engagement with this mobile app. So how often you're using it, how long it's been since you've used it. M is monetary value, which is how many miles a customer accumulates. So that's revenue to air miles. And then C is redemption. So I cash in points and get a reward. So we wanted to see how all of these things are affected by values in the previous period. So we ended up using a VAR model with one lag. We did various unit root tests to determine that was appropriate. We also threw in some exogenous variables, which include the age of the customer and how long that customer has been part of the Air Miles program. So just illustrating that you can control for these other factors. If we come down, you can see all of the estimates from our model. I created a presentation of this once, and this presentation, I think, really illustrates all of these coefficients more clearly than looking at the numbers. Green means positive, red means negative. So what this red line means is that the longer it's been since I've used the app, the lower my frequency of using the app. So that's kind of an obvious arrow. So if it's been a while, then I don't use it as much. What was more surprising was this arrow. So the longer it's been since I've used an app, the less I want to accumulate miles. So I don't swipe the card as much, which means less revenue for air miles. Now that's a very shocking finding, because it says if I download your app and then I don't use it, I have a disappointing experience. It harms the main part of the relationship. So I don't want to use air miles anymore because I've had a bad experience with the app, is what that's saying. And so the implication for that is you really had better make sure that an app creates value for the users, or you risk that negative effect. Let's go look at this other red arrow. This is saying the more I redeem points, the lower my recency. So that means I use this thing more often, more recently. All these green arrows are fairly intuitive. So the more I use the app, the more I accumulate miles. The arrow goes the other way. It's not quite as strong going the other way. Likewise, the more I redeem, the more miles I want to accumulate the next period. The more miles I accumulate, the more I want to redeem. And so we see somewhat of this virtuous cycle that's happening. There were some surprises, but that red arrow in particular was a big surprise. So I think this is a really ideal model for studying one of these dynamic systems. There's a lot more in the paper, and if you're interested, I encourage you to read it. That's it for my introduction to VAR models.